Failure, Pragmatic Lessons Learned the Hard Way. Or my subtitle there is Farm Life and Failure Reviews. As it turns out, Alan Willett and I, originally were colleagues starting out a few years ago, and Jeff Schwab got us together, and the trio has been together ever since. And so it's been exciting, but I learned that Alan and I were both farm boys. He grew up in Ithaca, New York, and of course I grew up in Southern Illinois. And so, in Southern Illinois, it's, basically you're either a coal miner or a farmer. And I decided to be neither one of those. And so it's actually a privilege for me to be able to talk about some of the things that I've learned over a 42-year career, a number of the failures that I've had, a number of the failures that I've been involved in the review process, documentation, writing, putting together books on how one does this. And so as part of my introduction, early in my career, I was an aerothermal structural analyst. And when I was working for the Navy or out here at China Lake at the time, I also had the opportunity to run our T-range facilities. T-range is a thermal testing range. It's a hot gas blowdown facility. So I was involved in what I will call the design, and you're analyzing a design with modeling. You go out on the range and you test it in this hot gas facility, looking at, we were looking at radome material testing, different airframe parts, so T-range job was to provide an aero heating environment based on time to these pieces of hardware. And that was my early days of understanding that failures can occur during these tests. The world does not end, and it gives you information to do a redesign. And so that was kind of etched early on. And so very early on in my career, but prior to my career, there was my farm life. So if you go to the next slide, Julia, appreciate it. So there's the outline. Farm life before engineering, be pragmatic. And the purpose of that is essentially use what you've got. Everything I learned on a farm in terms of, keeping the crops growing, keeping the tractors running and the plows working. Oftentimes you have to use what you've got. I've learned over 42 years to be humble and listen. I'll be the first to tell you, I don't know it all. So the next bullet down there is collaborate. A plan. So Mr. Schwab, I have been a student of his and the Carnegie Mellon Way a number of years ago, where we looked at, as a mechanical engineer, that's what I am, looking at how software is planned and written. And being one of his students for a number of years, we were able to adapt to this process to help create, in the department where I work, the Weapons and Energetics Department, a very good executable system engineering plan. And that has not always been practiced. Item number 6 there is Burr's Law. And these are some top level principles I'll share with you. Burr's Law is always stapled on my wall. It's actually next to me here in my office. I stare at that every day in terms of every project that I'm involved with. So I have a good understanding from the top level of what we're trying to accomplish in that project. And item number 7 there is a summary. So at the end of the day, here's what I'm going to leave you with. So if you go to the next slide, please. So what you see here is farm life before engineering, and small farm life is hard. And so you'll see a couple of insets there. There's a tractor at the top, which looks like a derelict. And that's essentially what happens to old tractors. You use them till they no longer go any further, and they simply die. And they're towed to a location, and that's where they begin to rust and go back to the earth. And so with that in mind, that's what I dealt with in terms of small farms that were all throughout Southern Illinois. And deadlines are real. When you're on a farm, the dirt gets plowed, the seeds get planted, and the harvesting occurs when the crops are ready to harvest. And at the end of the day, you're always battling the weather, because that very prescribed process of plowing, planting, harvesting, it's a set of steps that you have to do. If any part of that fails, the schedule is shot. Oftentimes the harvest is bad, and If you're a small farmer, that means there's no money coming into the bank if you can't sell a crop at the end of the harvest season. So, getting this done, getting the plowing done when it's supposed to, planting the seeds when they have to be in the ground, when the crop is ripe, it's ready to harvest. If the weather sticks its ugly nose in there any place, oftentimes, if it dumps a rainstorm during harvesting time and the ground is muddy, you can't drive a combine in the field because you'll bury it up to the axles, and then you're done. And so the harvest is shot, and it's a big loss of money. Item number 2 there is money matters. On a small farm, money is always an issue. So if something breaks, you simply can't buy your way out of a problem. That wasn't an option on a small farm environment. When you're working in that environment, if the tractor breaks, you as the farmer or one of the workers on the farm were required to fix it. There wasn't enough money in the bank to haul a broken tractor or a broken plow or something damaged on a combine to an implement dealer and have them fix it. So you were becoming the system engineer and the technician all at once, understanding how all this works. And so with limited bank account, you were really careful about, in the winter months on a farm, of servicing all of your equipment. And what you're trying to do, essentially from the system engineering perspective, is you're minimizing risk. If I do everything I can to make sure that tractor is in ready to go condition come springtime and plowing, then that's what I do. I use that to buy down my risk. And when risk goes down, the chance for failure also goes down. We also grew up with the idea of if you broke it, you had to fix it. And so the pragmatic approach there is, this is the real environment I live in. You use what you had. And so every small farm had an arc welder, it had an acetylene torch, it had scrap piles of metal, things of that nature. So if something broke, oftentimes we would take and trace out a part and go out to the metal scrap pile and cut it out and re-weld it into position to get things working and operational. So that's the real environment. That's what you had to work with. My last item there is, I call it my serendipitous introduction to system engineering. So in that lower right-hand corner, you see a magnificent tractor. It's a big four-wheel drive Allis-Chalmers brand tractor. And I was riding tractors and plowing fields back in the 70s. And so that was the very early days of corporate farming. And so here I am, I'm on my tractor, I'm driving, and I'm towing a 4-bottom plow. The tractor does not have a cab on it, so I'm in an open environment, driving up and down the field. I got a ball cap on, protecting my eyes from the sun, and you get the tractor noise and the blast of hot air coming off that tractor engine right back in your face. And so, you do this from sun up to sundown, and when the sun goes down, you turn the lights on the tractor, you keep plowing because you got to get it done. As I'm doing this, I look across another field out there in the open countryside, and I see a tractor just very similar to the one in that bottom right-hand corner. That is a beautiful piece of hardware. It has a cab on it that's air conditioned. It has a CB radio that you can connect to the farmhouse. It also has a radio in it, so you can listen to music or to the news or whatever. So you're in this air-conditioned cab. Life is good. But the small farmer could never afford a piece of hardware like that. So a piece of hardware like that back in the 70s, that was $150,000. That would be several $1 million today. And so you got an idea of, okay, here's what I have to do. In driving a tractor up and down the field, and here's the environment that we had to live with. And so when things broke, you had to fix it. You wished that you had enough money to be able to buy a tractor like that, but you knew that you never could. And so corporate farming, that was always the bane of the small farmer. So the big corporations with lots and lots of money could afford those kind of implements. And so that was my farm life. At the end of the day, sometime around the age or being a senior in high school, I stepped down off that tractor and decided I did not want to be a farmer. I did not want to be a coal miner. So I headed off to the university and I studied engineering. On to the next slide, please. So slide number 4, be pragmatic. understanding the operating environment, use what you've got. Again, being pragmatic. The formal definition is solving problems in a sensible way that suits the conditions that really exist now. That phrase in the sentence is critical, that really exists now. It's rather than obeying fixed theories, ideas, or rules. One of the jokes we used to make in my line of work as an aerothermal structural analyst and running physics-based models is that all models are wrong and some models are useful. Some of you know that. And so, we always had that as kind of a little bumper sticker in a lot of the work that we did. We knew that the models were the best that we could model at the time based on the physics that we knew. And so, that was one of the things that we walked into all designs with. So the subtitle there is called The Launcher Lessons, or When the Laboratory Meets Real Life.
Él no puede hablar ahorita. Él recibe, pues él no habla todavía.
Okay, I didn't get that as a question or not. That's okay. So my first item there is called the shoulder launcher. I would like to, it was a shoulder launcher was a weapon system at the time that when I was working for the federal government, DOD, we were designing, and it's a small missile. And is my camera working? If I bring this out in front, can you see this?
Yeah, we can see it.
So that's a model, the full-size model of the small missile. I gave about 8 to 10 years of my career in that weapon design. But the small missile was a potential to address the small boat threat. So if you look to that inset picture, first thing to the right, that is an Arleigh Burke class destroyer ship. There was one down in San Diego, and a few members of the design team were asked to come aboard the ship and look at our small missile that was in a shoulder launcher configuration, kind of looked like a bazooka. And we were using that to address the small boat threat. What they were doing before that was looking at what was the armament that was involved, or what was the armament aboard the ship. And so the ship has, multiple missile systems. They can launch mini missiles hundreds of miles downrange. And there was a phalanx, Gatling gun, a radar-controlled Gatling gun. There's a 30-millimeter cannon on board. And they actually had places to put 50 caliber mounted machine guns on the deck of the ship to protect the sides of it. And so that was the weapon systems that were on board. The insurgency had determined that the small boats, in large number of swarms, and these small boats were essentially 20 feet long, usually had a seat in the center of it. It was an open bow, a steering wheel, and an 80 to 100 horsepower Mercury outboard motor in the back end of it. Usually had a handful of what we would call insurgents armed with AK-47s and maybe an RPG. So for those of you that are not familiar, when a destroyer class ship like that, an Arleigh Burke, transitions from one large ocean body to another, there's usually straits that you go through. And this is where the bad guys would hang out. And they would send these waves of small boats out to come right up to the line where if they cross into that, they could be fired upon. But the ship never had the appropriate armament to address that small boat. So we thought we had the solution there. So I spent a day down in San Diego carrying a shoulder launcher to every location on that ship of how we might address and shoot the small boat. And one of the senior officers, we were below deck heading from the front of the ship to the aft end, and down a main gangway below deck, and we came across the battery shop. And I was feeling pretty good about myself because that shoulder launcher design was something that we had came up with, and I put a lot of work into that. So I was very proud of it, chest puffed up, feeling like quite the successful young engineer. So I met the sailor. One of the officers introduced me to the sailor who ran the battery shop, and he said, "Hey, show him your launcher." And so I very proudly handed over this prototype mock-up, and it had a battery system on it. And so he's asking me, he says, "What kind of battery do you have of this thing?" And I said, "Well, it's a custom design. We've got a design for what kind of power is required from this, and what's the current demand on it." But I said it's nothing that's in production, and it's not an off-the-shelf item. And so his expression changed. My smile and how how good I'm feeling about myself. He says, well, come on in. So I walked into his shop, his battery shop, and it was a 20 by 20, room below deck. And I'm looking around, and he said, he's holding my launcher, and he says, so do you see anything in this battery shop that looks reasonably close to that battery you've got in this launcher? And I said, well, no, I don't. So he began to read me the riot act, indicating something to the effect of, every battery that is aboard this ship comes through this shop. He says, I service them, I order them, I have them in stock. He said, that battery does not exist anywhere in this shop. And he said, and he asked me point blank, do you know how long it takes to qualify a battery to go aboard ship? So here I am. My proud smile and swagger is I've got drooping shoulders now, and I'm calling him sir. And I says, no, sir, I don't know. He says, it takes somewhere in the neighborhood of 2 to 3 years to qualify a battery to get this thing aboard ship. And I said, okay. And then he says, well, how long does it take you to design a battery to get it into production? And I had been working with Eagle Pitcher batteries in Joplin, Missouri. And I said, I'm $8 to $10 million and 2 to 3 years on their calendar to design this thing. And he said, so this launcher that you've got here is essentially, it makes a better anchor than it as a useful weapon for addressing the small boats. So after I had my backside handed to me and I walked out of that shop, I learned that I did not understand the operating environment from a logistics perspective, that what I considered to be that great design was not going to work unless I considered the entire engineering life cycle. That was a wire brush across my backside that I never forgot that one. The next story that goes with this and understanding the environment and what can cause failures is the airborne launcher. And so the small missile who I introduced you to a moment ago was about to meet an unmanned air vehicle. And so what you see in the in the pictures on the side, the insets, you'll see a Predator UAV. General Atomics manufactures those. It's built about 150 miles south of us down in Rancho Bernardo near San Diego. And what you'll see under the left wing is a Hellfire missile. The right wing has an empty missile station, so it's fired one. And so our small missile was going to look at addressing something called the the asymmetric target. And so the asymmetric target, as the Army as well as the Air Force had presented to me, was essentially it's a very used Toyota Hilux truck with a handful of insurgents who are armed with AK-47s, potentially an RPG, and maybe a small caliber machine gun riding around in that. And so that's a target, it moves, and it's called asymmetric. And they want to kill those asymmetric targets. And so the weapon of the day on unmanned air vehicles was Hellfire weapons. Hellfires are magnificent pieces of hardware. They're designed as an anti-tank weapon, designed to go after main battle tanks, and they leave a very satisfying smoking crater in the ground. But their cost is about $100,000 each. And so the military was asking, do we have a less expensive way of dealing with the asymmetric targets? So once again, we showed up with our small weapon design that was perfect for addressing something like that, our small missile. So the picture on the right is a helicopter. It's a Vigilante helicopter. This was owned by the Army. It was out of Fort Eustis, Virginia. So I'm out here at China Lake, California, and Fort Eustis is, absolutely on the other side of the country. And so we essentially negotiated a deal to where we would look at integrating our weapon system, our weapon, onto that helicopter. And what that required was there was no airborne launchers that existed at that time for our small missiles. So that was another design that we had to do. And so it was about 6 to 8 months from the original design to getting that on the helicopter. So the helicopter was out here at China Lake, and we were getting ready we had a missile out on the launcher. We were sitting out on the tarmac, out on the range early in the morning, and our pre-launch procedures of the steps that we had to go through was approximately an hour long. And so the launcher is sitting out there in the sun. The sun is up over the mountains and it's shining on it, and it's turning into a nice warm day. So we got green range, which means everything's in place. We have a limited time that we can go out and shoot a target. So the helicopter lifts off, it's making its way to the target. It does a couple of passes. It's ready to, we're ready to pull the trigger, fire the missile, and blow the target up. And so in my launcher design, there was a detent mechanism that was required to hold the missile onto the launch rail. And it was simply an electric plunger motor that had limit switches on both ends of it. And so you would release the detent, the limit switch would say it's lifted up out of there. And so that would switch a light to green on the launch panel that says missile is ready to fire. You hit the button and you fire it. So making a hot pass, the command, the permission to fire was given, and they were trying to remove the detent and it would not come up. We had a red light. And we made several passes and we were still not able to fire the missile. So the helicopter comes and lands. EOD is there. They take the missile off the launch rail, put it back in the box. And the chief engineer who was there in the control room gave me a look and he said, let's go for a walk and talk. And so there were a number of inflectives communicated back and forth with him and my design, and that you're never going to work in this town again. And so, you got to figure this out because we got to try to fix this problem and fly in a couple of days. So gathered the team together. This is very early stages of doing failure reviews and looking at models of the design. And our model was correct. The mechanical model and how it operated was correct. What we didn't do was apply the appropriate boundary conditions. And so we didn't understand that operating environment. With sun shining on one side of the launcher and shade on the other side, I had a delta in temperature across that. And so the temperature on one side of the panel of the launcher, the panel was actually a structural member. So coefficient of thermal expansion, as temperature goes up, it begins to expand. And that temperature difference from the hot side to the cold side was enough to tweak the internal structure and jam up the plunger on the limit motor to remove the detent to fire the missile. So that was another, I'm not sure we'd ever caught that one in the design phase of that, because I never ever thought about that in the environment that we were working with. But what we learned from that is that small missiles, small parts that have very, very fine tolerances, when they're working and everything is, temperature is kind of the same all through it, life is good. But when you get temperature deltas in very small things, coefficient of thermal expansion can be a big enemy. And so that was a great lesson learned of understanding that operating environment. Julie, if you go to the next slide, please. Be humble. Listen carefully to others. So my subtitle there is the murder board, or the more politically correct department review, is very critical. I was now, at this particular time in my career, I was the chief engineer for the weapons and energetics department, very new to the job. And so my department head indicated that every project that was going on in the department, and we had 1,100 people in the department, and my job was to have some insight in overseeing the engineering that was going on for all of the projects. So we had a big investment in a project, and where we were putting a fiber optic laser system into an MH-60 helicopter. So that picture inset is MH-60. And so that was the airframe that we were trying to mount a laser in. And you're asking, why would you put a laser into a helicopter? So back in the early days of directed energy, about a decade and a half ago, directed energy was considered to be the bottomless clip. And so I'm not firing bullets, I'm directing energy and firing energy pulses at targets. And so, hey, I don't run out of missiles, I don't run out of bullets and have to go back and refuel and reload. As long as I got fuel, I can keep firing. Great theory, but it doesn't actually work that well in operation. So the project was a fiber optic laser was the name of the project. And the goal was to put that laser system into the helicopter. Excuse me. And they were having a lot of problems. It's like you show up to the meeting, you essentially invite yourself to the team meeting, and you show up and you're sitting at the head of the table, and you discover that there's 30 other people sitting around the table with their heads tilted back, their arms folded across their chest, leaning back in their chair, staring down their nose at you. And it's like, why are you here? And, oh, you're the person who's supposed to come and fix our issues because we're failing. And so my skin got kind of thick in those days of being able to take some sharp looks and a few bad comments on occasion. But as I began to dig into this project and looking at the planning in the project, and it had a lot of flaws, or a number of flaws, was small business contracts, or SBIRs, were part of the design phase of creating the laser system. Different small businesses were doing the frame for the laser to sit in, the cooling system for the laser, the focusing lens for the laser, the power system. And they, as I began to dig into this and review it with the system engineers for the different contracts involved, you would learn that communication was not there. They weren't listening to each other at all. And it culminated one day as the group that I was working with here at China Lake, or on the days when I worked on center at China Lake, they took me out to a hangar out at the airfield, and they had an MH-60 airframe, and they had a mock-up of the system to date that they were trying to insert into the airframe. The Navy wanted this to be a palletized approach. So basically a laser on a pallet. You can take a forklift, lift it up and slide it in, attach it to the deck, and the laser head would descend through that hole in the floor of the helicopter to be able to address targets. And I'm there looking, I'm staring at the open door of the helicopter, I'm staring at the mock-up that they've got. I asked that question that you see as bullet number 1 under item 1. Did anyone measure the height of the door? They didn't. And I simply walked over to a tool chest and got a tape measure. I went over and measured the helicopter door height. Then I went over and looked at the platform that they were going to mount the laser on, their mock-up. And there was an inch difference. Guess which inch difference it was? The mock-up laser was an inch taller than the door. And so that was a failure in the early design of the project. Mr. Schwab and I actually consulted on that one, and we kind of went through the early phases of a good engineering design that was not practice in those stages. And so again, bad system engineering design, bad communication with the other folks involved with it. And there was, my sub bullet at the top, listening carefully to others. That wasn't going on. There was poor communication. So flawed from the beginning, high risk involved when you have bad communication, poor project plan. And so at the end of the day, it was a failure. You could not fit the laser onto the helicopter. And as you all know, when you have a failure like that, if you're going to fix it, it's calendar time to go back and redesign. And a redesign of that magnitude was going to be well over a year. And it wasn't going to be a few $100. It was several $1 million to go back and do a redesign. So significant cost and significant calendar time to do a redesign on that. And that's how projects oftentimes get canceled. And so that was an introduction to me early on as a chief engineer of, we need to do some things about this. Next bullet, item number 2 is, I just need a safety release and a trigger. So this goes back to our original design for our small missile, and looking at the shoulder launcher design of this. Basically looks like a bazooka. And our design, we thought, was very magnificent. We were very proud of it. As engineers, we designed it, and we sit behind a desk. You look at Pro-E renderings of models and how all this is going to work. And, we think we've got the design well understood, good review process. And we had installed in this launcher a number of switches. You had this, I got to turn power on. I've got to look through the reticle to look at the target. Does the missile see the same target as my eyeball does? So I have some adjustments to make on gains if I need to. And then I remove the safety, or release the safety, and I squeeze the trigger and fire a round downrange. And so we went through and looked at, there was about 7 steps that one had to take before you could send that round downrange. So at China Lake, we have what is known as a Marine Aviation Detachment. So it's a detachment of Marine pilots. and they had a gunnery sergeant there who had been in combat. And so we thought we would be clever to see how good our design would be to show this to the Marine, the old gunny, and let him take a look at this and see what he thinks. And so we're getting some input from an end user. He took a look at this and he asked a question after looking at this for a few moments after we went over how this functions. And he asked a simple question: have you ever been in combat? Of course, I'm a civilian. And I said, no. And then it was like, no, sir. And he said, I have. And he said, when people are shooting at you, he says, your IQ drops to single digits. And he said, I do not have time to perform 7 sequential operations to get this thing operational, to pull the trigger, send a round downrange to engage a target. And he says, did you not ever come and think to talk to an end user first who has experience in this area? Again, the little subtitle above is, we didn't listen to the appropriate people in the beginning of this. So after we had this input and, the pride in your design now, after having a real end user look at this thing, you now have made pages worth of notes and you go back to the design, which is not uncommon in the world of weapons, going back and repeating a design cycle. But I was learning about what you do first to minimize the chance of failures. And my bumper sticker down at the bottom of that slide is, listen very carefully to others, as there is great knowledge in an experienced group. I never forgot that one. So that's what connects to that top line, the murder board or the department review. All projects at that stage of the game in my early years as chief engineer in the department would go through a review process with some very crusty, seasoned engineers in the department that had a lot of knowledge that spanned a lot of years, who have seen problems and can look at a design very quickly and say, this is going to be an issue or this is going to be a problem. So my goal at that point in time was, if we can scrub these designs early on, then we can minimize the risk of failure, and life gets good for everybody at that point in time. So let's go to the next slide, please, Julia. So here we are at collaboration and talking with others. My subtitle there is, I don't know everything and I'm not afraid to admit it. Systems are very complex, and system of systems, as the military uses or DoD uses today, to describe the very complex systems, are make it even more complex. A system of embedded systems to make a weapon system function. So very early, so I've got about 10 minutes, so I'm going to pick up the pace here. Very early in my career, a couple of my colleagues that I had actually went to college with, I was a mechanical engineer and they were both electrical engineers. Very early on in the design of the small missile, we would get together after work hours in one of their offices on a whiteboard, and we'd sketch this missile system out. Between their 2 electrical engineers as their expertise and me as an ME, we used to joke at one point in time and says, hey, the 3 of us made one pretty good engineer. And so that was my initiation into, I don't know everything, and it is great to have trusted colleagues sitting at your side who have experience, which leads me into the next item 2 there is, here's my design, throw some rocks at it. So the previous slide, back at that department level review or murder board where your initial design is shown, I would go through this first wire brushing with a small group of engineers, excuse me, to get their input into my design and to look at, this is not going to work. You're going to have some issues here. My experience on another program has told me that here's an issue or a problem area. So let's fix it now before we spend any money or get too far down the road. And we know this design has high risk and it's going to, again, I use the word fail. And so that also was introduced into the department as a way to fine tune our projects and make them better initially before much money got spent. What had to occur is, and I use this as me, my skin got thicker, and we used to joke about filing injured self-esteem complaints to our supervisor. And so that never happened, of course, but your skin gets thicker, your self-esteem no longer gets injured, and you listen carefully to these folks about how to improve a design that's in the conceptual stages. Another, and of course, to add on to that, item number 4 there is, don't forget to visit the end users. I learned that over a period of years, and a number of designs that I put together that were mechanical designs that required, the use of electronics in it, the double E portion of this. And they would tell me, well, how am I going to get cabling? Is there cableways in this? And so, a rendering of a Pro E design, I get technicians involved to take a look and say, can we build this? Or, is this simply, the way this thing is modeled, there's just no possible way to get fingers in there to install parts, to run cables, to do things like that. So again, you're at the early stages of a design, you're trying to minimize risk and utilize the folks around you. You're collaborating with others to help make your design better early on, again, minimizing failure down the road. So my bumper sticker there is a community of trusted engineers who tell you the unabashed truth is great for innovation. Next slide, please, Julia. Thank you. The plan. So I'll be very short and quick in this slide. So as my chief engineer job, I ended up doing a number of fairly large scale failure reviews. And I suddenly said, I'm the failure review guy. How did I get here? So the first one I did was hard. I was terrified, and it goes back to one of our small missile designs that had a fail out on a test. And we were shooting a missile in the middle of the night using a laser to illuminate the target. It failed. And so we all, go home at 3 o'clock in the morning. We're back in the lab at 8 a.m. in a conference room. And the chief engineer looked at me and he said, I'm going to put you in charge of doing this failure review. I had never done one. I was terrified. And so I nodded my head and said, yes, I'll do that because I didn't know what else to do. So I read everything I could on how you do failure reviews. I spent time reviewing what NASA has done, some of the major aerospace contractors, how they do business. I finally made my way successfully through this review. I documented everything that I did. The review ended up being about a 50-page document. When it was done, the chief engineer says, I want you to present this to the team as well as our senior management because nobody ever does that. So I put together this report and did a presentation to our senior management in putting these results together. And I had no idea, but at that particular point in time, nobody ever documented and saved these reviews. They were sort of lost by the team. The issue was fixed, we're on to the next thing, and no one ever had a clue or a plan of how to do failure reviews. So after I did about a half a dozen of these, I began to get proactive versus reactive because I could see the early stages of a project, bad planning, bad communication, bad, things that were, potential to go wrong, as opposed to doing failure reviews where I'm reactive. Let's do a better job in the beginning of a project. And so again, this is where I teamed up with Mr. Schwab and some of his team. And you'll see in the beginning, a good system engineering plan is critical to success. And that's the goal, to bring a project in on cost, schedule, and meet its performance ways. The Carnegie Mellon way is not, we'll start writing code on Monday, as was communicated to me by Mr. Schwab and a few of his team members. And so, we began to adopt that approach, and software planning is we were using that to plan projects. We modified it to fit the scope and the size of the project. So that was the plan. It's essential to preventing failures from occurring down the road. And some of my experience with many programs that were research programs, my bumper sticker at the bottom says, you can't fix a program that's 4.5 years into a 5-year delivery without egg on your face. And so, when someone comes to you after 4.5 years of working on a project and we're not going to meet our delivery date, can you take a look at this and fix it? And most of the time you can't. And so you stand there with large quantities of egg on your face. So we began to be working that proactive approach to, instead of having a failure, let's fix this in the early stages. Next slide, please. Burr's Law, I used to keep this in my back pocket. It's on my wall. I use this as a way to, look at a top level view of a project. Can you answer these questions? What are you trying to accomplish? what's your approach? What are your measurable short-term goals or milestones? How will you measure performance on your project? And how will you know when you're done? Item number 5 is always a critical one. As an engineer, I like to engineer things to perfection. In the previous slide, cost, schedule, and performance is a big driver. And so with enough money and enough time, we can get warp drive. But can we do this in a reasonable amount of time for a reasonable amount of money, which most projects are controlled by? Those become the limiting factor. So let's go to the next slide. So let's bring this home. One of the things that I have learned, the smoking gun, and Alan Willett and I have had many discussions about this. The smoking gun is usually the cause when you're in the middle of a failure review. What I have learned in running a number of failure reviews, in fact, many of them, failures can come in many forms. They can be engineering performance failures. And so you're looking at engineering tests and you're learning something from that. Is my design good? Does it work, etc.? Oftentimes failures that are missile systems that are tests for score, does it work properly in a developmental or operational test? And it fails, there's lots and lots of money, lots and lots of people involved, and generally admirals are involved and are not happy. So it's a highly emotional environment when something happens like that. So if you're leading the failure, you have to be the calm that's in the middle of this storm. Quickly, I learned when you come in as the calm, you have to get item number 3 is don't point fingers. Just because your portion of the design may not have contributed to the failure doesn't mean you've earned a lot of swagger and, I didn't fail, you did. And, that you're trying to create a cohesive team to solve a problem and resolve this so it doesn't happen again. We always try to teach in failures, accept the failure, learn from it, grow. There's pain in growing sometimes, and yet at the same time, be very humble. Overcome the fear of failure such that innovation is not lost. Some people become so failure adverse that they're afraid to innovate and do new things with weapon systems. So accept failure. Oftentimes it's a bloody nose, but you shake that off and you keep going. The most critical thing I've ever learned in failure reviews is write it down. Otherwise, it's lost until it reoccurs. And I say reoccurs with multiple explanation points because I've been involved in failure reviews where the same thing has occurred again. And so if it's not written down, if it's not well documented, that other people can have access to it and to learn from it, it's lost. And those few people that were there when it occurred, that bit of tribal knowledge is lost. And it's so valuable to be able to have archival records of things like that they can be retrieved and looked at so that it can help in the future. My bumper sticker there is, if failure occurs, what doesn't kill you makes you stronger. So thank you for listening. If you have any questions, be happy to answer them. Thank you so much.
Okay, so I think you can feel free if you have a question to unmute, or if you'd like, you can also put it in the chat. So people are clapping. So Rick, I have a question.
Sure.
A lot of the problems, failures that you talk about are like, missed requirements. Have you had situations where you've had requirements that just weren't valid? That, somebody wanted something that was either technologically unimportant or, maybe somebody wanted something and then that person's gone, it didn't make sense. And how would you handle that situation?
So so that's a very good question. And yes, I have addressed some of those problems. One of the missile programs that we worked on was to be adapted from an F-18 who has a set of specific requirements and loadouts for this particular air-launched missile system. They wanted to put it into an internal bay on an F-35. And so an internal launching bay, of course, gives it low drag on the aircraft as well as a low RF reflection image. And so lots of money was being proposed, and there was millions to go back and do some redesign because it was a canard controlled. We're going to make it tail controlled. And so it's a huge redesign of the weapon system. And I was looking at a lot of drawings. I got asked as chief engineer from the department, the missile program gave me a call. And I'm reading through requirements and looking at drawings. And again, this takes me back to, did somebody measure the door? And I said, I'm staring at the door of the F-35, this enclosed bay, and will the missile fit in there? And so the famous line that I uttered that it was not very popular was that one of the chief engineers says, well, it should fit. I think it should fit. And, there's a small group of us sitting in a room. And I said, the difference between I know and I think is years on the calendar and millions of dollars in a budget. So the simple story is they went and measured it and said, it won't fit. We have to reduce the length of the missile by 6 inches. And of course, that is a catastrophe. And so, yes, it occurs. And I said, way back here in requirements, we went back and reviewed the requirements for the F-35. And I said, it states right here how big a weapon system can fit into this enclosed bay. So yes, it occurs. Requirements always have to be looked at, especially if you're trying to adapt something a little different into an existing system.